Now we see square planar complexes with formula with metal atom and 4 different ligands as A, B, X and L. All these are unidentate ligands. So in this sort of square planar complexes, we are having the 2 possibilities of cis isomers. Let's first see how the naming is done. We select it on the basis of the atom binding to that metal atom. For example, in pyridine, nitrogen binds to platinum. In ammonia, nitrogen binds to platinum. And then next here, we are having a chlorine. Here we have bromine. So accordingly, we assign priorities. In this cis isomers, what we will see, we see the heavy elements like bromine and chlorine are on the same side, and lighter elements will be on the other side. So we see here basically their geometries or the arrangement will remain the same. They are on adjacent sides. That's why it makes a cis. In trans, what we see, the heavy elements are opposite to each other. So it makes it up our trans geometry. So this is example of cis and this is example of trans. Here we are having a possibilities of 3 different isomers. And remember, we have the unidentate ligand atoms or ions, and we assign the priorities on the basis of this binding atoms to metal. As you just saw, 2 cis and 1 trans isomers possibility in case of MEBXL sort of square planar complexes. Next, geometrical isomerism for octahedral complexes with the molecular formula metal atom X2 mean 2 ligands will be of same type and 4 ligands L4 will be of other type. Here we see an example of Cobalt Complex. We are having 4 ammonia molecules here. You see, this is the same plane and these are axial positions. You see in a equatorial plane 4 atoms. Out of 4, 3 are ammonia, 1 is chlorine. So here chlorine and chlorine atoms are very close to each other, they are adjacent. So the 2 out of 2 atoms, they are very close to each other and it makes a cis geometry. And in other side, when 2 ligands occupy our axial position, we get trans isomer. That's the example. Similarly here, we see we having 3 cyanides and 1 ammonia group occupied in octahedral plane. An axial position is occupied by ammonia as well as cyanide group. In trans position, both ammonia groups are in axial position. They are 180 degrees apart. All cyanide group occupied equatorial plane. So these are the examples of MX2 alpha sort of complexes. Now, next isomerism is for octahedral complexes having MX2 where X is a unidentate ligand and LL which is didentate ligand, mean we having 2 didentate ligands and 1 unidentate ligand. Let's see an example. First, these octahedral complexes. Trans mean same like in what we saw earlier, that unidentate ligands occupy axial positions. This is a cobalt tetramine dichloro complex. This is a trans. Next is, what happens? One of the axial position is occupied by one of the nitrogen atom of didentate ligand, which is diamine, and chlorine occupies one of the equatorial plane position, so it's adjacent to chlorine. This is called cis complex. This is a cationic complex, so name will be now another example of octahedral complexes, which are Ma3, B3, mean we having a 3 one sort of ligands and B another sort of ligand, so 3 both. This is the first example. What happens here? Here 2 ligands ammonia occupies the equatorial plane and 1 axial plane. Similarly, 2 ligands occupy the equatorial plane and 1 axial plane. Same way. So each sort of ligands, if we join together, we are getting a one sort of face. See here, one face sort of thing we are getting, one face like structure by joining all these. It's called facial, because it's making a face of one side of octahedral. Similarly, if we join ammonia here, we are getting a one face. It's a facial octahedral complex, or one's facial isomer is a one category of geometrical isomers. Another complex, what happens when 3 molecules occupy the same plane, like nitro group here occupies the equatorial plane and ammonia groups are in our axial positions, and only one ammonia is present in equatorial plane. So here we make a face in equatorial plane. It's called meridional because it's occupying only in a single plane. Another category of isomerism is optical isomerism. So optical isomers are mirror image that can't be superimposed on one another. These are also called enantiomers. So beauty of optical isomerism is the compounds having a similar structure, they only differ in the 3D arrangement of molecules in space in such a way that if we take a mirror image of one compound, we get in another compound, but the mirror image is not superimposable on the original compound. Here we have a mirror. Now, these compounds having a one beauty, no property, that they rotate the plane polarized light. If you remember earlier, we discussed about the plane polarized light. It is a single plane, and if that plane of light we pass through this compound solution, it will rotate either to right side or left side. If the plane polarized light is rotated toward right, it's called dextro, and if it rotates toward left, called leavo. Easy way to remember, you can remember because both left and leavo having the first letter L. Here we are having a cobalt complex with this is triose, clean diamine. So what happens? If we take a mirror image of this compound, here we get a mirror image, exactly a mirror image. Here ammonia is back, this is back, same bonds are back, and this is in the coming front, right? Is coming front, and this is in, these two nitrogen atoms are in axial positions. But even if we try to rotate it or superimpose this compound over this one, it will never superimpose, you remember, because these bond positions will change. We will never able to superimpose this structure over this structure by any rotation. Let's say if we rotate it, these are okay, same, but here carbon atoms or this ethylene group in the other side, this is in the other side. If we rotate it, okay, like here, if we rotate it, it will go toward the back. It will never superimpose on the other atom. So this is a dextro form, this is a leavo form.